Imagine learning mathematics from a book that refuses to explain itself. One devoid of proofs, no derivations, just results. Page after page of formulas waiting to be understood. But for a young boy in southern India, it became a doorway to an entirely new way of thinking about numbers. Patterns that repeat, patterns that reveal unexpected symmetries in the realm of the infinite. Srinivasa Ramanujan wanted to know how numbers behaved. And in this strange mathematical universe, he discovered some of the most beautiful identities ever written. And this is the story of the Modular Mind of Ramanujan. Consider the improper fraction 271 divided by 43. And instead of converting it to a decimal, let's investigate its structure as a fraction by using the Euclidean algorithm and getting a whole number part and a proper fraction part. Next, if we take the proper fraction and invert it, its denominator is now a new improper fraction. And if we take that new improper fraction and split it into its integer part and a proper fraction part, we can then take this process and repeat it over and over again until it reveals its layers. It reveals a nested structure called a continued fraction. And this simple finite continued fraction can be written in shorthand as follows. You see, continued fractions are one of the most beautiful ways to understand numbers.
He was, in a way, my discovery. I did not invent him. Like other great men, he invented himself. The difficulty for me, then, is not that I do not know enough about him, but that I know and feel too much.
Finding patterns in irrational numbers. So let's take the square root of 2, which has a value between 1 and 2. We can write it as 1 plus a fractional part we'll call r0. And if we solve for r0, we get the square root of 2 minus 1. Now, taking the reciprocal of this, we rationalize the denominator, and that allows us to split this into an integer part plus a fractional part, and that becomes 2 plus a fractional part. Solving for that new fractional part, we realize that it's equal to the square root of 2 minus 1, which is equal to our original fractional part. This creates a closed loop, and therefore we get to construct an infinite periodic continued fraction, one with a simple notation here using a bar notation to represent the continuity of the 2 in the denominator. A pattern in the irrational numbers reveal themselves through this beautiful structure. So what would be the value of the simplest infinite continued fraction? Well, 1 with all 1s, of course. So consider the continued fraction given here, and we'll call its value x. Now if we take x, and we find the reciprocal of both sides of that equation, we get this expression. And then if we add 1 to both sides of this expression, the right-hand side is now the same expression as x. So we get a closed form equation, an algebraic equation, which if we rearrange it is a quadratic equation, which has a solution of 1 plus radical 5 over 2, the famous golden ratio value. So the simplest infinite continued fraction is equal to the golden ratio, which begs the question, what do functions look like as continued fractions? Alright, let's start with the transcendental function e to the x and its beautiful power series to create its continued fraction. The first step is we're going to take the 1 in the power series and subtract it to the other side. Then on the right hand side we're going to factor out the leading term x, which will then leave a new infinite series. As a result, we'll call that new infinite series a of x. So now this infinite series is one that we're going to take its reciprocal, and we'll call its reciprocal a new infinite series b of x. So now we want to determine what that new series b of x looks like, so that we can build a preliminary structure for e to the x. Alright, so a of x and b of x satisfy the equation that when you multiply them together, they equal 1. Since we know what a of x looks like, and we create a preliminary structure for b of x, we know that multiplying both sides together on the right-hand side must match the coefficients on the left-hand side. So all the coefficients, the coefficient of x and the coefficient of x squared, are both equal to 0. So we can use that to solve for b and c and other coefficients if you wanted to for the series b of x. So in doing so, what we find is that b of x is equal to this new infinite series. And therefore, again, we have a preliminary structure for e to the x. To find b of x, we'll do a linear approximation, or to first order. It looks like 1 minus x over 2. And so we can get a general form for the continued fraction form of b of x. And again for e to the x. So if we iterate this process, as a result, we will get a function in continued fraction notation for e to the x to look like this. And if we evaluate this at x equals 1, we get an expression for this beautiful transcendental constant, e. Of course, if we found a continued fraction for e, we must find one for our favorite mathematical constant. That's right, in celebration of Pi Day, let's find the continued fraction for pi by tapping into the arctangent function. In a similar spirit to e to the x, we take the arctan power series and factor out its leading term, yielding a new series, a of x. A of x is this now power series, which, if we look at just the variable part of the series and rename that variable part u of x, we can then factor out its leading term and get another new series, b of x. So now we have this power series for b of x. And now we have a structure for a of x when we take its reciprocal. And as we do this, the character of the continued fraction takes form. One can't help in watching the systematic beauty of its construction. And of course, all we're doing is iterating the process over and over again, looking at the new coefficients, factoring out the leading terms, and building an overall pattern that only within a few layers will begin to reveal its structure. And finally, after one more or two layers in our continued fraction, we get a continued fraction form for the arctan function of x, where you can see a beautiful pattern of odd numbers as well as squared numbers in the expression. So now we can make the generalized principal value of this continued fraction to be as follows when we plug in x equals 1. And by plugging in x equals 1, the arctan of 1 is equal to pi over 4. So multiplying both sides by 4, we have this beautiful expression for pi, one that shows off its connections to some of the most famous and well-known numbers. The mathematical influences of Leonhard Euler. Euler was a mathematical wizard, and he developed an intimate relationship with the sine function and its power series. So, dividing this expression by x, we get a new power series which is representative of the function sine of x divided by x. Now, Euler let x equal the square root of y and created a new power series in this new variable. And then he asked the strange question, what are the zeros of this function? Well, since the zeros of this function are the same as asking, what are the zeros of the sine of the square root of y? Euler knew that he had to solve this equation to get the answer. And so, this equation has solutions in the way of square integer multiples of pi squared, with the exception of 0. And he connected this to the idea of finite polynomial zeros, which had n roots. He knew that the coefficients had something to do with the roots, and therefore he thought about rewriting this function in its factored product form. And since the coefficient of x, the a1 coefficient, is the negative sum of the reciprocals of the roots, he would use the solutions to this equation and find its a1 coefficient to be negative 1 over 3 factorial, or negative 1 over 6. And this is where the magic happens, because this coefficient is also equal to the negative sum of the reciprocal of the roots of his product function. And therefore we get this relationship, which allowed Euler to solve the famous Basel problem, which was to find the sum of the reciprocals of the integers squared, and it led to this transcendental value. But this wasn't the end of the magic of this function in its product form. Rewriting this product in big pi notation, which is used for infinite products, one can use the value of x equals pi over 2 in this formula to obtain what is known as the Wallace product for pi. Observe. By plugging in pi over 2, we get this relation, And we're going to simplify the fractional part and evaluate the left-hand side to be equal to 1. In our product, we get the simplified form 1 minus 1 over 4n squared, which we can combine to be 4n squared minus 1 over 4n squared. We can then take the reciprocal of both sides of this and get this new product, which is equal to the pi over 2 of 4n squared over 4n squared minus 1. Now, if we factor that, we can write this as 2n over 2n minus 1 multiplied by 2n over 2n plus 1. And writing this product out explicitly, we get what is known as the Wallace product for calculating pi.
But I hadn't completed that proof. How do you know?
I don't know. I just do.
Shifting our attention to another one of Euler's creations, the Euler product. At first glance, this expression seems almost too simple to be interesting, just an infinite list of factors. But Euler wondered something curious: what happens if I actually multiply it out? What becomes evident is the absence of certain powers of Q. In fact, a pattern begins to reveal itself in the exponents. You see, the exponents form a sequence. Let's call this sequence P sub n, and these numbers, it turns out, are called the pentagonal numbers. So what does this series have to do with a pentagon? Creating pentagons with points, each iteration increasing the number of dots along its side by 1, creates a sequence called the pentagonal numbers. So now if we use the formula that Euler found for the pentagonal numbers in his exponents, we can generate a list for each sequence. And by each sequence, I mean one for the positive integers and one for the negative integers. So for the positive integers, we get the list 1, 5, 12, 22. And for negative integer values, this formula reveals the pattern 2, 7, 15, 26, so on. Combining these two lists together, we get what are called the generalized pentagonal numbers. Now this gives Euler the idea to dissect his product into what are called residue classes modulo 5. So let's list the elements of each residue class modulo 5. So by taking a number and dividing it by 5, you can get one of 5 different remainders: 0, 1, 2, 3, or 4. This gives us the 5 residue classes modulo 5, which we'll denote here with a square bracket, 0, 1, 2, 3, and 4 being our classes modulo 5. So generating the elements of the residue classes modulo 5, that is, listing the elements in each residue class, really just amounts to counting by 5s. And that is, we can list every integer as some element of one of these residue classes. Now, listing each element in the residue classes allows Euler to rewrite his product by slicing it into sections via residue class. And so his infinite product is sliced up into 5 parts. And to make some of the notation a little bit easier, we'll introduce what's called the Poshhammer symbol for infinite products such as these. So Euler's product can be written in terms of the slices given by each Poshhammer symbol. So now Euler dissects his product mod 5. He wants to understand what the slicing would do to his series. So separating out the terms in the series by their exponents according to modulo class 5, he deconstructs his series, E of Q, into the following parts. Euler was able to write an identity equation, noticing clearly that certain residue classes were missing, those classes being the classes 3 and 4 modulo 5. So now, if you look at the first product in our dissection, we notice that this is just merely the Euler product evaluated at q to the 5th power. So dividing out by this product gives us slices, which we then pair off into 2 parts and package them into 2 objects. We pair residue classes and package them into the objects P of Q and Q of Q. Thus, our ratio can be written as the product of these 2 functions. Now comes the strange question. What happens when you compute the quotient P over Q? In other words, what happens when you take the slices that have been paired off, and maybe ask the question, why have they been paired off this way? Well, one notices that the pairs in the numerator constitute the quadratic residues mod 5. The ones in the denominator are non-quadratic residues mod 5. So we're looking a little deeper into this ratio as to why the slicing is made as it is. So now we have these 2 infinite products, and we're looking at their product as the ratio EQ over EQ to the 5th. And what we'll do now is take these 2 products and define 2 reciprocal series, G of Q and H of Q, so that H over G is equivalent to P over Q. More on that in a few minutes. To fully appreciate mod 5 symmetry, we look at a pentagon on the complex plane, formed by the 5th roots of unity. Those are the solutions to the equation x to the 5th minus 1 equals 0. With one root anchored on the real line, the other 4 roots are complex, and they form the vertices of a pentagon, some of these roots being complex conjugates of each other. And by multiplying by a root of unity simply rotates you through a 72-degree angle around this pentagon, inscribed inside of a unit circle. And thus, we get a sense of some kind of mod 5 symmetry in a geometric sense. So if our ratio function is to be well behaved respecting mod 5 symmetry, then through each rotation, Q would pick up a phase factor of this root of unity. The weights of the numerator and the denominator of our ratio function picking up these phase factors will cancel, and our function will be globally balanced. That is, taking the quadratic residue slices in the numerator and the non-quadratic residue slices in the denominator creates the weights that balance out the function, this ratio, in a global sense of its symmetry, mod 5. Balance and symmetry were very important to Ramanujan in his equations. So now all we have to do is look at what this function does at its smallest level. That is locally. At the smallest exponent level, Ramanujan would use logarithms to explore the ratios as series. So taking a logarithm of this ratio p over q transforms it into a power series. And when you compute the first few terms of this power series, the smallest non-zero power of q is q to the 1/5. So this determines a natural local parameter for the ratio. This function is now both globally and locally balanced. And this is the Rogers-Ramanujan Q function. And it's literally something that Ramanujan used like a magic spell. And it's got a lot of secrets to tell. Ramanujan realized that by taking ratios of these mod 5 slices, entirely new functions could emerge. Those infinite product forms and those infinite series forms he knew could be transformed into each other. And between these forms, he would discover new truths that conveyed to him the thoughts of God. Okay, so recall the Euler identity we came up with earlier. And we found the ratio E of Q over E of Q to the 5th. So if we wrote that out explicitly, our product P times Q, which is the ratio of 1 over G times H, is in fact this ratio EQ over EQ to the 5th.
Now you've begun to embrace some proper rigor. I think you should meet Major McMahon. He's the leader in combinatorics at the university and also happens to be one of your most vocal opponents. He says partitions can't be done, especially by the likes of you.
Then you better start counting very high.
So why such an interest in functions like these? Well, to answer that, we have to answer what are partitions. And that takes us back to the Euler product formula. Euler also investigated its reciprocal. And as always, he expanded it into a series, with a little help from the geometric series given here. So the reciprocal product becomes a product of series. But when this product of series is actually multiplied out, the way that the components multiply reveals something very deep. The way that the exponents add when the terms multiply showed Euler that the coefficients were encoding the way of counting something about the number exponent. To understand this a little further, a partition of a number n is a way of writing n as a sum of positive integers. So if we take the number 4, we see that there are exactly 5 ways to write 4 as a sum of positive integers. So we create p of 4 equal to 5 and call it a partition counting function. It counts the number of ways the number 4 can be written as a sum of integers. And it turns out that the coefficients of q in this reciprocal series count exactly the number of partitions of the number that represents the exponent.
Enter at your own risk.
Ah! I've been waiting for you. Square root of 58,639. Now!
242.
242 what?
0.1549090.
Yes, child's play. Try me.
Go on.
Same number squared.
3,438,532,321. Ah! Thrashed you! Combinatorics, that's what I do. Glorified dice throwing. Bloody nerve of you both. You fail on primes, then you think you can just turn round and crack partitions. Can't be done, I'm telling you. Especially not by you.
It can. And I will.
It would be Ramanujan's collaboration with G.H. Hardy that brought his genius to the world's light. Central to Ramanujan's way of thinking, to create ratios of mod 5 slices to see what other secrets they hold, he would now use the product form of h of q and g of q to examine what they would look like as infinite series. Something in true Euler fashion. So in product form, we can take their ratio and look at what that has in terms of a pattern when we multiply things out and then see what the series on the top and the bottom look like. So first, Ramanujan would take this infinite product and look at the first couple of terms in each of these expansions. So if we expand it out, what does that look like? In investigating, Ramanujan was much like a detective where he saw patterns after looking at evidence. And so the top and the bottom products give us a little bit of evidence to look at in their exponents. Ramanujan developed the Q series for both G of Q and H of Q. And one notices that both of these series have the same denominator structure. And that's a key thing to notice, because if those series both have the same denominator structure, taking their difference is something that is very easily computed. Because the difference here now will also have the same denominator structure. Ramanujan saw this as a repetitive pattern, a recursiveness that is occurring, which reminded him of the continued fractions he studied in his text as a younger boy. And so he began to take this difference and factored out the leading term and noticed that the series that resulted also had the same denominator structure. And so by, let's just say, calling G equal A and H equal to B, we can do a series of deconstructions which are similar to the continued fractions we saw earlier in the video, and we can construct a continued fraction for this Rogers-Ramanujan Q function. And one notices that at each level, we're scaling up by a power of Q. And so, in constructing this continued fraction, Ramanujan really saw what the layers were speaking to him about, a rescaling of the values. And that to him meant that the modular function that he was creating had a deeper type of symmetry to offer. And eventually, he found the ratio G over H to be this continued fraction, where each layer has a new power of Q. And by taking the reciprocal of this ratio, and then multiplying by a prefactor of Q to the 1/5 power, Ramanujan had found a continued fraction that rescaled itself at each layer of its nested fractions. This was something magic, and he didn't stop there. Ramanujan still had questions about his new entity, questions about symmetry, identity, and ones that commuted revelations. Exploiting the power of complex exponentials. A common value for Q in a Q series is the gnome Q equals e to the 2 pi I tau, where tau lives in the upper half complex plane, meaning its imaginary value is greater than 0. So working in the upper half complex plane, what is our new continued fraction function going to do when we plug in this value of Q? So applying the gnome to Q transforms it into a complex function of tau, we'll call lowercase r of tau. And we want to consider transformations of tau, such as translation of 1. So by doing a translation of 1, we notice that the gnome Q returns to itself, Q. So we're wondering, does our new function of tau do exactly the same thing under this type of translation? What does this translation really do? Well, Q lives on the unit circle, which means that these transformations take place on a unit disk in the complex plane. So when Q rotates around the origin once, we pick up a fifth root of unity as a multiple. So translation by a factor of 1 indicates that we are rotating around that unit circle. Now, another type of transformation we think about is complex inversion. S of tau is -1 over tau. And that's because at tau equals I, this particular transformation has a fixed point of that transformation and will lead to a fixed point equation later on. So the upper half plane H has a symmetry group called the modular group, PSL2Z, and the generators of this modular group are translation by 1 and complex inversion. So the modular group acts on tau via something called a Mobius transformation. So what is a Mobius transformation? A Mobius transformation is a fractional linear transformation, sending tau to a tau plus b over c tau plus d. And this corresponds to a matrix with a determinant of 1 of 2 by 2 entries with integer values. So the translation can be viewed as this Mobius transform and the translation matrix given here. We can do the same for inversion. Inversion -1 over tau corresponds to this map and this matrix. So Mobius transformations are just fractional linear transformations where the determinant of that matrix is 1. And actions T and S are the generators of the modular group, the projective special linear group of 2 by 2 matrices with integer coefficients. It's the special linear group modded out by the double cover given by plus or minus the identity. So what is this doing? Well, it takes values that lives on a lattice in Q and outputs them onto the Riemann sphere. So let's investigate what that means. On a lattice or a complex torus surface, we take input values. The output values are transformed onto something called the Riemann sphere. It's the complex plane wrapped up into a sphere, including a point at infinity, which I know sounds strange. But the union of the complex plane with infinity creates a sphere on which we can do geometry. And so transformations on the complex plane in tau translate to translations of r of tau. So how do transformations of tau transform r of tau? First, through translation, we know that it rotates r of tau around the sphere by a fixed angle, given by a root of unity, a fifth root of unity. And inversion, well, that's an interesting one, performs an inversion of the unit circle plus a reflection. So under this inversion, points near infinity move towards the origin and vice versa. In other words, it swaps infinity with 0. So on the sphere, inversion creates a Mobius map of the function r of tau. And if inversions take far points and near points and swap them, and left sides and right sides and swap them, essentially what we're doing is just changing the directions of the lattice. And on the Riemann sphere, Mobius maps correspond to rotations, reflections, or combinations of both. In other words, the symmetries of the sphere. Now, S is something called an involution, meaning when you apply it twice, we get the identity. This corresponds to a 180-degree rotation about an axis on the Riemann sphere. And from geometry we know points along an axis of rotation remain fixed. That's why there are 2 fixed points that this Mobius map will induce. So points along the axis of rotation remain fixed. And thus we want to find the map, and thus those fixed points. And that map we'll call f of x. And under inversion, we know that these things called cusp values at 0 and infinity will get swapped. So our lowercase r evaluated at infinity corresponds to our capital R evaluated at 0, which is equal to 0. And then under inversion, infinity and 0 swap, changing q to the value of 1, and therefore we can get r of 0 equals capital R of 1, which is equal to 1 over the golden ratio. So inversion gives us 2 image points of our map, our Mobius map f of x, the one that we're trying to determine for our function r of tau. But we need 3 image points to determine this map. So our last one will come in the way of the translation map. Recall that the translation map of tau will pick up a root of unity for r of tau. Thus, r of 0 equaling 1 over phi means that r of 1 is going to allow us to solve for r of 0. And thus, under this map f, we can invert 1 and 0. In a sense, we can also get the value of r of 1. But it turns out that r of negative 1 is simply 1 over our root of unity times the golden ratio. So under inversion, we get a 3rd image point for our function f of x. F of the root of unity divided by phi is equal to 1 over the product of the root of unity and phi. Now, one thing to consider about this map is that it is pretty much invariant under a scaled multiplication of the coefficients, which leads us to be able to be free to multiply both the top and bottom of our function here by 1 over d, which will essentially transform our function to have a free variable, meaning that we can choose d equals 1 in our map. Thus, we only need the 3 image points to determine the 3 other coefficients in this map. So f of 0 is equal to 1 over phi, which is equal to beta, and thus we can refine our map to read as follows. Now we have 2 coefficients to determine. Taking our second image point, we're going to determine alpha, and alpha here will turn out to be negative 1. So now refining our map by inputting that value, we have one more coefficient to find, gamma, and using the third image point for f, we can determine that value with a little bit of algebraic manipulation. And thus we can turn this equation into this equation, which we can then use a property of the roots of unity and its reciprocal, and rewrite this gamma also using a property of the golden ratio, and simplify it to be just 1 over phi. So our map is now complete, and we can simplify it by multiplying top and bottom by phi to give it a more simpler version. Now this Mobius map applies to R of tau. So we have this fixed point equation to work with. And this is exactly what Ramanujan would do by exploiting the fact that inversion has a fixed value at I. And that leads to a fixed point equation, which is really a quadratic equation. And the solution to this quadratic equation gives us the value of R evaluated at I. And it leads to something involving the golden ratio. Now, because R of I is a positive value, we're interested in its positive root. But we can simplify this expression by also using a property of the golden ratio itself. And thus we can write R of I as negative phi plus or minus the square root of phi plus 2. And again, we want the positive root because this is going to represent a Q value of e to the negative 2 pi. So in the world of Q values, we have e raised to the negative 2 pi, a transcendental value. But it's producing a very algebraic output, one that involves the golden ratio 1 plus radical 5 over 2. And just to see the true algebraic nature of this, and how just very strange this expression is, in our continued fraction, we get the expression to look like this, with transcendental inputs. But its value, that Ramanujan was able to show, is equal to the fourth root of 5 times the square root of phi minus phi, which is this value if you write everything out. And with that, Ramanujan becomes a wizard in the world of mathematics, as Euler did, by finding these miraculous connections with just a little bit of modular thinking. And it's to that end that genius only requires a shift in perspective.
It is difficult to put into words what I owe Ramanujan. His originality has been a constant source of suggestion to me ever since I first met him. And his death is one of the worst blows I have ever felt. But now I say to myself when I'm depressed, and I find myself forced to listen to tiresome and pompous people, well, I've done something you could never have done. I have collaborated with both Littlewood and Ramanujan on something like equal terms.